We have today a recorded talk of Yee Park about the Naruse hook-length formula for Skew shaped tableaux.
Thank you, Lara. And throughout the talk, if there's any question, feel free to interrupt me. Okay. I'll be talking about Naruse hook-length formula, and this is the overview of the talk. So first, we'll go through some background information and talk about the hook-length formula for the straight shape tableaux. And then I will introduce a Naruse hook-length formula that came out pretty recently and talk about its generalization to mobiles, which I will define in the talk. And if the time permits, I'll also talk about the qanalogue and the brief method of proof of the theorems. So first, a Young diagram is let lambda be a non-increasing sequence that represents a partition of n, and we can represent this partition as a Young diagram. So again, if my n is equal to 7, 3 plus 2 plus 2 is 7, and 2 plus 2 plus 1 is also 7, and I can represent that as a diagram shown here below. And you guys can all see my mouse as well. Okay. And given a Young diagram, we care about hook length. So hook hook length comes from a cell, hook length of a cell is the sum of the number of cells below and to the right of the cell and the cell itself. So if you look at this cell, the green one, there are 2 pink cells to the below and 1 yellow cell to the right. The pink cells represents lambda sub I minus I, and the yellow cell represents the lambda sub j prime minus j, and the +1 is the cell itself. So this is the hook. It's literally a hook. And the hook length then is 4. Now that we have a Young diagram, we can fill them up and make standard Young tableau, which is the filling of lambda with 1 through n such that it is increasing both in rows and columns. So these are 2 examples of a standard Young tableau of shape 2, 2, 2, 1. As you can see, each row is increasing and each column is increasing for both the cases. We care about the number of standard Young tableau because one of the reasons is because it gives a dimension of irreducible representation of the symmetric group induced by lambda. So for example, in S3, there are 3 irreducible representations: trivial representation, which is represented by partition 3, sign representation by 1, 1, 1, standard representation by 2, 1. And we already know that the dimension of trivial representation and sign representation is 1. And there's only one way to fill out these Young diagrams so that row and columns are increasing. As for 2, 1, there's 2 different ways as I shown in the pre-seminar. And indeed, the dimension of standard representation is 2 in S3. So counting this number is important. And in 1954, Frame Robinson and Thrall came up with a famous hook length formula. And we can count the number of standard Young tableau by taking a product over the hook length of each cell. So for example, for our case 2, 2, 2, 1, the blue entries are not the standard Young tableau. They're not increasing by rows and columns. These are the hook length. So again, this hook is length 4. Take 7 factorial, which is the size of the Young diagram, 1 over the product of all the hook lengths. This is 14, and there are indeed 14 standard Young tableau for the shape. And this hook length formula has been studied very extensively. So now that we have a hook length formula, we'll be talking about Naruse hook length formula. And to do that, first I have to introduce skew shapes. So skew shape is a pair of partition lambda and mu such that mu is a subset of lambda. Basically, you draw lambda as previously, and then you take away mu from the corner. So there are 3 examples here of the skew shape. Lambda is 2, 2, 2, 1 as before. The first example we have mu is just 1. So you just take away this corner. I colored it in green, but you can treat them as if they're not there. For the second example, mu is 1, 1, 1, and as you can see, it can be disconnected. It's fine. And for the second one, it's 1, 1. And we'll be focusing on a specific type of skew shape called border strip, which is a connected skew shape without any 2x2 squares. So the first one, we have a 2x2 square, so this is not a border strip. The second one, there's no 2x2 square, but this is disconnected. So this is also not a border strip. The third one, indeed, is a border strip. So you can kind of, this is literally a thickness 1 strip. And then again, given a skew shape, we can also fill them 1 through n, but except now the n is not the size of lambda, it's the size of lambda over mu. Again, increasing both rows and columns. Is there a question? Chat. Oh, okay, thank you, sorry. Yeah, so then this is the first one is Standard Young tableau of this shape. You fill it up till 6, not 7. The second one also is increasing by rows and columns. And then the third one is also a Standard Young tableau for this shape. And again, we would like to count them. So for the case 2221, there are exactly 9 of them, and all the examples are shown here. But unfortunately, there's no hook length formula for the number of standard tableau for skew shape. Before, I think it was the size was 7 and the final product was 14, and 14 definitely divides 7 factorial. Here we have 9 of them of size 5, but 9 does not divide 5 factorial. So there's something a little bit weird going on here. So we couldn't, there's no hook length formula for this one. Until Naruse in 2014 came up with his own formula, which mimics a hook length formula, except you sum it over these objects called excited diagrams, which I will define next. And the original proof was very complicated using a lot of algebras and representation theory, but a combinatorial proof by Morales, Pak, and Panova has, based on the case of just a border strip, was introduced in 2019. So let me explain the excited diagrams. You obtain them from performing excited move. So given a skew shape, color in the mu parts, and you can perform excited move onto these mu's. There's a lot of words here, but basically, given a colored cell right here, if to the right, to the bottom, and to the diagonal is available, then you can slide it down diagonally to this box. So, for example, in this case, let's look at the first cell. We cannot perform excited move on this cell because the bottom cell is not available. So we can apply excited move onto this second cell. So we slide it down and we obtain a new excited diagram. Now this guy cannot go anywhere else because it's cornered up. But now this guy can move because everything has been emptied out. So this also moves diagonally to the down, and this is a new excited diagram. And the process terminates because these colored cells cannot go anywhere else. For the case of border strip, which is the one that's shown here, there's another way to interpret excited diagrams. It can be seen as a number of lattice path from the most southwest corner to the most northeast corner. So if you just look at the white part for each of these diagrams, there's one way to get from here to here is through that path, or through this path, and finally this path. So there's a bit more combinatorial interpretation to excited diagrams for border strip case. So let's do an example for the Naruse hook length formula to convince ourselves. The case of 2221 over 11, we have obtained the 3 excited diagram, which is shown below. And again, the blue entries are not the Standard Young tableaus, but the hook lengths of each cell. Note that hook length of each cell, no matter what excited diagram there are, is a hook length of the lambda. So for this one, it's still 4, regardless of the skew shape, because we're looking at the hook length of the lambda. So we take 5 factorial because that's the size of lambda over mu. This fraction corresponds with this excited diagram. This fraction corresponds with this one, and this fraction corresponds with that one. add everything up, and we have 9, which was, and I've shown you all 9 standard Young tableaux of this shape in the previous slide. Is there any questions so far? Okay, so now let's generalize it to mobiles, but in order to do that, let me talk about linear extensions. So given a poset, linear extension of P is the, oh yeah, sorry, was there a question?
Yes, so I was asking if the number of standard Young tableaux of skew shape factor nicely into small prime factors.
So like there was the formula that involved the sum, which doesn't suggest that they would factor, but the example 9 is a nice number. I'm saying, is it an accident? Do you find something like, 37 at some point?
So 9, but the 9 still does not divide by factorial. Sorry, what was the question?
It wasn't if they divide the factorial, it was if they themselves, those numbers, are nice factored numbers.
Oh, yeah. Yes, and I don't think that is a coincidence, because at the end we still need like a nice integer number, but I don't know. I haven't looked at the actual proof of the general Naruse formula, so I don't know if that's actually a coincidence or if there's actual like combinatorial or representation meaning behind that number.
But Guy, a comment, like if you want a 37 as a factor, then you need to have 37 factorial. So,
Or,
but I thought you had the sum of things in the formula, and I was thinking, right, there is a sum of things, and I was thinking that maybe.
Yeah, I don't know if it's a coincidence or not. Yes, okay. So let's move on to the linear extension. Linear extension is a linear order of elements compatible with the order P, as is shown in the pre-seminar. So for this poset A, B, C, D, the linear extensions are A, B, C, D, and A, C, B, D. And we care about E of P denotes the number of linear extension. So for this case, E of P is equal to 2. And I would like to now relate the posets to tableaux. If you take this poset and rotate it a little bit, you can see that it resembles the tableau, Young diagram ABCD as shown here. And let's look at one of the linear extension ABCD. That is like saying A is in the first position, so the entry of A is 1. B is in the second position, so the entry of B is 2. C is in the third position, and then entry of C is 3, and D is 4. And there's another one, ACBD, and same thing. B is in the third position, comes in here. B is the third position, so then entries of B is 3. C is the second position, so the entry of C is 2. And indeed, these two standard Young tableaux are the only standard Young tableaux of this shape also. And the very fact that A has to come before B and C is equivalent to the entries of A has to be less than B and C for the standard Young tableau. So given a tableau, we can always relate it to the poset, and counting the number of standard Young tableau, for the shape is equivalent to counting the number of linear extensions for that posets. So in this case, this is my previous example of the skew shape tableau. Take this, rotate it a little bit, make a poset out of it, and any linear extension of this poset is equivalent to the standard Young tableau of this shape. And so, because they're the same thing, E of P, the posets derived from a standard Young tableau, is equivalent to number of standard Young tableau of that shape. So the question is, are there other posets with a Naruse hook length formula generalizing the formula for number of linear extension? So what I mean is, on one hand, we have this thing called border strips. So we can count the number of linear extensions of the border strips using the Naruse formula, like the one that I introduced before. And then on the other hand, we have these Young diagram posets that you can derive from Young diagrams. And because they're from the Young diagrams, they have a nice hook length formula. And if you combine them together, we have something called mobiles. And the question now is there a nice formula to count the number of linear extensions for mobiles? So mobile was defined by Garber, Grosser, Mathern, and Morales. It's a poset obtained from a border strip lambda over mu by hanging the complete posets to it. So as you can see, this is a border strip, and you hang all these D-complete posets like Young diagrams to this strip. And when I was giving this talk last week as a practice to my friend, he was like, oh, like baby mobile. And I was like, you're right. It is like baby mobile. And I didn't realize that it was named after mobile. I never questioned it, but it made so much more sense when I realized what a mobile actually was. And we are going to be talking about freestanding mobile, which means that we are only hanging it downward like this. So we fix the direction. So I've been talking about Young diagram, and now I mentioned the complete posets. So the complete poset is a large class of posets that basically behaves really nicely. So it has the hook length formula to count the linear extension. So one example is Young diagram, like the one that I've shown before. Another example is a rooted tree. Rooted tree also has a nice hook length formula, and also shifted Young diagram also has a very nice formula. And Peterson and Proctor has claimed that indeed all of these posets, number of linear extension, can be counted using this same hook length formula, except now the definition of hook may change depending on which diagram that you're using. For Young diagrams, hook is, as you already know. But for rooted trees, hook is defined a little bit differently. It's a number of elements that's descendant or equal to it. So for example, if we want a hook length of this element, there are 2 elements below and 1 itself. So this hook is now 3. Let's look at the hook length of this guy. Because there's now 3 arms instead of 2, you'll be counting all of these elements plus itself, which is an entire poset. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and this hook length would be 10. And they also came up with a nice determinant formula that actually generalizes the formula for the linear extensions for these mobile posets. And they also ask if there is a Naruse formula to it. And I was able to, and then now this is a Naruse formula. Again, we are summing it over the summing it over the excited diagrams. And again, product of 1 over the hook. And we now have to redefine hook for mobile posets. Given a border strip, if we are to get a new hook of each element, it is the original hook plus the size of the D-complete posets that is being hung to the right and to the below. So to the below is this pink line, and to the right is this pink line. So this shaded, highlighted area is the area that we are looking if there's a D-complete poset being hung on any of those things. So there are 2 D-complete posets being hung, but only this one is in pink. So we are only going to count this when we want to calculate the hook length of U. So the original hook length was 3, but now because we are also counting in this D-complete poset, which is of size 4, we have to add, and a new hook length is then 7 for that element. So let's do an example. Let's take the exactly same border strip, but let's hang a small D-complete poset, specifically this tree, to this and see if the formula works out. The black vertices 1, 3, and 1 are not changed because to the right and to the below, there is no D-complete poset that's being hung. The red ones, though, are the ones that do get altered because of the D-complete posets. So this element, which is equivalent to this vertex, hook length was originally 2, but now it gets shifted by 3. And each of the red vertices also gets shifted by 3. So if you, again, plug it in, this one is all the hook length for this excited diagram is written here. And this is also corresponding to that excited diagram. That one also corresponds to this one. If you add everything together, you get 184. And that indeed is the number of linear extension for this particular poset. Is there any questions? So we have a little bit more time, so I can go to the qanalogue of this. So the qanalogue is over the semi-standard Young tableau, which is a Young tableau with strictly increasing columns, but weakly increasing row. So the diagram here, to the right, it was our standard Young tableau, but to the left, we have a semi-standard Young tableau because the first row is now not increasing anymore, and there's repetitions of entries, so this is not a bijective filling anymore either. And the size of this standard Young tableau is the sum of the entries. So for this standard Young tableau, there's 2 1s, 2, 3, 3, 4, 4. So the sum is 18. And I talked about short function during the pre-seminar. And now short function also can be defined as a generating function of semi-standard Young tableau. And we can replace the Young tableau by skew shapes to obtain skew short function. We can also take it to its qanalogue by replacing the variables x0, x1, x2 as 1, q, and q squared. And this is the qanalogue version of the generating function of SSYT. And Stanley has come up with a qanalogue version of a hook length formula here. There's a little extra factor here, b of lambda, which is just a sum of I minus 1 times lambda sub I. Now for the poset, the qanalogue of the number of linear extension is calculated over a labeled poset p comma omega. There are mainly 2 types, the major index and the inversion. I am probably dropping too many informations here, but the specializations of the short function is given as a major index of a labeled poset. So I will only mention the major index qanalogue. The major index of the permutation is a sum of the position of descents in the permutation. And such permutation comes from the linear extension of this labeled poset. And there's a qanalogue Naruse hook length formula for skew sure function, which is also summed over excited diagrams, and also one for the labeled poset. And you can see there's a lot of relations here. A of D is a broken diagonal, which I will not be defining for this talk, but the equivalence of that object in a mobile, which counts now all the complete posets as well. You can see the relevance in the mobile poset as well. So there's a couple more minutes, so I can talk about the method of proof briefly. So they defined a multivariate function f of x and y, and this is just a definition. But if you plug in the correct x and y, in particular, so that x minus y is equal to the hook length, then they have this equation. So to get the x minus y to equal to the hook length, they just take the original equation for the hook length and they partition it into nice parts, x and y, and plug it in. And then once they have that, now they also have recurrence property of a standard Young tableau, which is shown in this lemma here. Given any skew shape, to build a standard Young tableau, you label one of the inner corner as 1, then fill out the rest as the standard Young tableau of the smaller shape. So for example, for these 9 standard Young tableaus, there are really 2 types. The one that starts with 1 in this corner, so the top layer, and including this middle one, all the standard Young tableau starts with 1. Or you can have 1 on this corner, which is the bottom layer. So you fill out 1 here and fill out just the 4 squares as if it's a standard Young tableau of size 4, and you've obtained a standard Young tableau of size 5. So all standard Young tableau of skew shape can be defined like this, and there's a recurrence formula that is written here. And now they define the recurrence property for so then they have to make sure that the recurrence property also works for this equation. And they checked it combinatorically, which is the reason why the border strip matters here. And this is a Tableaux formula for the border strip. And once they check the recurrence property for this formula, all they have to check is check the Naruse formula inductively, and you will get the final answer. And yeah, and then that is it.